Welcome to the introduction for thin layer chromatography. For the first 4 experiments of this semester, we'll be exploring various separation or isolation techniques common to synthetic organic chemistry labs. For the first experiment, we'll analyze a mixture using thin layer chromatography. Specifically, we'll be looking at a mixture of 3 compounds: fluorine, fluorinone, and benzoic acid. Next week, you'll work to separate fluorine and fluorinone from benzoic acid using a process called liquid-liquid extraction. So at the end of next week, you should have 2 components, the first containing fluorine and fluorinone, and the second, which will contain benzoic acid on its own. In the third experiment of the semester, you'll take your first mixture, fluorine and fluorinone, and separate those from one another using column chromatography. At that point, you will have isolated fluorine. In other words, you will have pure fluorine in hand. And the same for fluorinone. So you will have 2 pure compounds arising from that initial 3-compound mixture. Our 4th week will focus on benzoic acid, and we'll use a process called recrystallization to ensure that any remnants, any minor impurities that might have been present are now removed such that we end up with very pure, high-quality benzoic acid. So again, we will start with a mixture of these 3 compounds and work to separate them out to their individual constituent parts using a variety of separation, isolation, and this week, analytical techniques. And again, we'll be starting with a procedure called thin layer chromatography. So I want to provide a bit of historical context for you. Chromatography was first developed by Russian botanist Mikhail Tsvet in the early 20th century. He used this process to separate plant pigments such as chlorophyll or other similar highly colored compounds by passing a solution of these pigments through a column packed with calcium carbonate. He found that different pigments moved at different rates, forming distinct bands, which he described as a chromatographic effect. Fast forward a few decades, and we see Martin and Singe begin to improve upon and expand this technique beyond just botany. So they began to use paper as the so-called stationary phase and some form of solvent as the mobile phase. So the stationary phase, as the name suggests, stays still, while the mobile phase moves over it, effectively carrying the chemical compounds across the stationary phase. They discovered that this was a very valuable tool for separating and identifying biomolecules, such as amino acids and carbohydrates. The same pair also worked to develop gas chromatography, a process that we will touch upon briefly later this semester. And in this case, the mobile or moving phase is gas rather than a liquid solvent. Collectively, their work was awarded the Nobel Prize in Chemistry in 1952. If we move forward through the decade and on to today, we see the advent of incredibly high-powered techniques such as high-performance liquid chromatography, which was developed in the 1960s and 1970s and helped improve the speed, resolution, and sensitivity of liquid chromatography. And then we also see a variety of more sophisticated detectors, columns, and stationary phases. This is an incredibly powerful technique for synthetic organic chemists and is one of the most common methods that we will use this semester and that you will see in any chemistry-based research. Specifically, we will be looking at thin layer chromatography, But in a few experiments, we will be using column chromatography, and even later still, we will look at something called gas chromatography. Now, each of these look very, very different on their face, but they all abide the same basic principles discovered by Tsvet and then expanded upon by Martin and Singe so long ago. If you plan to take analytical chemistry down the line, you'll go into great detail on the theory behind chromatography. For our purposes, we're going to keep it fairly surface level because we're really interested in the more practical aspects. What can this tool do for us? What can we achieve with it? So I'm going to give you a very high-level overview. You can imagine a stationary phase. So this is really just a non-moving phase, we'll call it, that is going to be used to help separate out various compounds. So if we were to take a compound mixture and then put that mixture into some form of mobile phase, so as I mentioned, that mobile phase is sometimes solvent, so liquid, but it might also be gas, as in gas chromatography. So that mobile phase will carry the compound mixture down across the stationary phase. And as it moves down, different compounds will be attracted to the stationary phase more than others. So I almost think of it as a bus. They will get off at various points and then move more slowly than some of their counterparts, which are effectively carried further, faster down that stationary phase. So if we look at this cartoon diagram, we can say that the compound that stayed on the stationary phase the longest, right? If we use that bus analogy, it's sort of the one that got off the bus first. This compound has the greatest affinity for the stationary phase, or we can also think of it as having the lowest affinity for the mobile phase. Of course, if we go to the opposite end, we see our compound at the far right, which would have had the lowest affinity for the stationary phase. It was the least inclined, so to say, to stay on the stationary phase. It had the lowest affinity for. Alternatively, you might consider it to have had the greatest affinity for the mobile phase. It wanted to stay with that mobile phase as it moved along the column or along that stationary phase. So let's take a closer look at our technique for this week, thin layer chromatography. Again, you'll more commonly hear this referred to as TLC, which is what I'll call it for the rest of our lecture today. TLC uses a typically, though not exclusively, polar stationary phase. This is often an adsorbent, for example, silica gel, and is supported on a solid back. You'll sometimes see glass, plastic, or even aluminum backings. In this lab, we'll use plastic. So onto this stationary phase, we will load our compound or mixture of compounds. So here I have a mixture of compounds 1 and 2. And then we will add into this a mobile phase. And if our stationary phase is polar, we will use a non-polar mobile phase. In this case, TLC will use a solvent mixture that's used to then carry our compounds across the stationary phase. So as the mobile phase moves up the stationary phase, we see that our compounds get off at different points. They travel different distances across the stationary phase. And that distance traveled depends on both the polarity of the compound and the polarity of the mobile phase or the solvent system. And this is where it's very useful to remember one of our favorite phrases in chemistry: like dissolves like. The more polar the mobile phase, the more attracted polar compounds will be to that mobile phase. So to help optimize the rates at which our compounds travel up the plate, or the distance at which they travel up the plate, we can toy with our solvent system by combining nonpolar and relatively polar solvents. And I want to be careful here because our stationary phase is really quite polar when we use, as we will, silica gel. This is a very polar stationary phase. So although our mobile phase or our solvent system will have a polar solvent in it, it is nowhere near as polar as the stationary phase. So that's a really important point to consider. Relatively speaking, our mobile phase is nonpolar. But within that nonpolar mixture, we can modulate the extent of its polarity or nonpolarity by mixing a nonpolar solvent with a polar solvent. So if, for example, we look here at this first plate, this is where we would consider a mobile phase to be too nonpolar. Okay, so our stationary phase, the plate itself, is highly polar, which means that our compounds are very attracted to the plate itself, right? That's why they are not traveling very far off of their origin point, or as we call it, the baseline. They're staying there because they are more attracted to the very polar stationary phase than they are to the non-polar mobile phase. Now, on the other side of the spectrum, we can envision a case in which our mobile phase is perhaps too polar. In this case, our compounds were very attracted to the relatively polar mobile phase and worked to travel their way up all the way to the very top of the plate or the end of our plate. In an ideal world, we'll modulate the ratio between our nonpolar and polar solvents such that we end up with clean separation between our compounds. Here we have this mobile phase just right. Our compounds are attracted just enough to the plate, our stationary phase, but also just enough to the mobile phase, our solvent system, such that we get this really nice separation. So there's a distinct affinity difference between compound 1 and compound 2. I'm not going to walk you through the entire protocol here, but there are a few things that I want you to take a look at before you embark on your own experience with TLC. You're going to begin by making a solution of your sample and dissolving a very small amount of it into a solvent. TLC is a very sensitive technique. You really only need a very small amount in order to get a good data point. So you'll have your plate and you're going to gently sketch a faint pencil line about 10 millimeters from the bottom of the plate. Be sure to draw on the silica side of the plate and be very careful. You want this to be a very gentle pencil draw. If you go too hard, you risk scraping the silica, which will, of course, impact your results. You can either draw a very small pencil dot. I prefer a small line perpendicular to the larger baseline that we've just created. And this is going to be our origin or our starting point. You'll then lightly dip a TLC capillary tube, more commonly called a TLC spotter, into the solution containing your sample. And then you'll hold the spotter upright and very quickly and gently dab 1 to 2 spots right on that center dot. Assuming you've used pencil, the pencil will not interfere with your compound, will not interfere with your data. Let's just take a quick look at what we mean by this gently, quickly spotting your plate. If you let too much of that solvent solution come out onto your plate, you will end up with a very big spot, and this will cause some interference in your data. So really, you're looking for a quick, gentle dab 1 or 2 times to get the smallest diameter of spot possible. The smaller the spot will lead to a clearer spot once it has run up the plate with the mobile solvent, as compared to a larger spot in which you might see what we call a trailing spot, which is not as valuable overall. So to run your TLC, you'll first begin by preparing your TLC chamber, a small glass jar with a lid. You'll place a piece of filter paper vertically along the wall of the chamber, and then you'll add your eluent, which is just another word for your mobile phase or your solvent system. You'll prepare and spot your TLC plate, as we just described, and then you'll gently place the plate into the chamber and allow the solvent to run up the plate. Now, as you do this, I recommend first that you use forceps to both place the plate in and then later to retrieve the plate from the TLC chamber. I also encourage you to be very mindful. You don't want your plate to touch the walls of the chamber as best you can avoid it, and you definitely don't want your plate to touch the filter paper that you've placed in there. So really, it should just be touching at the very bottom of the chamber, nothing else. And I'll note here that the eluent or the solvent in your jar should be below the line on the plate when you first put it in. So in picture 3, you can see that our solvent line, right, the point at which the plate is wet, is higher than our pencil baseline. So this is a TLC plate that has already run for a few seconds. When you initially put it in, that solvent line must be below your baseline. You'll let it continue to run until it's about 10 millimeters from the top. At that point, you'll take your forceps, carefully remove your plate, and use your pencil to very quickly draw a line across the top where the solvent stopped. This is what's called the solvent front. Once you give your plate a few minutes to dry, you can then bring it under a UV lamp to visualize and then circle the compound spot. So picture here, we have a plate that is under a UV lamp, and you can see that spot glowing under UV. We would then take a pencil, very gently circle or trace the spot, and the point of this is that we want to be able to remove the plate from the UV light and still know where our compound ended up on the plate. And of course, requisite warning here, UV light can inflame or burn your retina. Please do not look directly into our lamps, and please ensure that you are turning them off when they are not in use. At that point, you'll calculate our TLC data point, which is the retention factor, or RF. So this is really the key. This is what we are after when we do TLC analysis. So to calculate the RF, you are going to take the ratio of the distance your spot has traveled, which I've marked here as A, over the distance the solvent traveled, so the distance between your baseline and the solvent front. Because this is a ratio, it is unitless or dimensionless. Very best of luck with your first organic chemistry laboratory experiment, and we will see you next week for extraction.